Afternoon, everybody. Welcome to another Learning at Lambert Labs session. And this week's presenter is Rafiq. So I'll hand over to Rafiq.
Thanks, Evan. I will share my screen. Okay, so today I'm going to be presenting on how to execute code asynchronously using the asyncio package, which was introduced to Python, I think, in Python 3.4 as a built-in package. So the first question would be, what is asyncio? What is asynchronous execution, and when should we use it? So for the overview, asyncio enables concurrency. So concurrency is the concept of being able to execute multiple different jobs at the same time, although not necessarily at the same time, but kind of they don't have to be executing in parallel. They just have to be, they can take turns at executing. So parallelism is a slightly different concept, which is saying that two jobs are executing at exactly the same time on, say, different cores. So the approaches to writing concurrent code are threading, where you take multiple threads and they take turns executing tasks, which is good for input-output tasks, but in Python, it's actually pretty difficult to do, and it can be quite error-prone. You can get errors which are very hard to debug. The second approach would be multiprocessing. So this is a parallel form of programming. And when you do this, you spread tasks which are kind of tightly bound across multiple cores. And that's suitable for CPU-bound tasks. And then what we have with asyncio is asynchronous coroutines. So it's a form of cooperative multitasking. And what we do is we execute tasks in a concurrent manner, but on a single thread as a single process. So this is not parallelism because all of the tasks are taking turns on a single thread. And it's not the same as threading because it is only on one thread and not multiple threads. But it's great for IO-bound tasks. So what makes asynchronous code? So an asynchronous coroutine, which is very similar to a function, must have the ability to pause while it waits for the result. And it can allow other routines to run in the meantime while it's waiting for that result. And then asynchronous code is just code written in a manner that it can run these asynchronous coroutines concurrently. And when should you use it? So generally when tasks are input-output bound, so making requests to a server or writing to a file, and any of these tasks which you can run, run other tasks while waiting for the result. So how do we write asynchronous code? So we have this async keyword. So when we're defining a function or a coroutine, we put async at the start of it. And we get this async def for defining the function. We can use the keyword await in it, which we'll cover in a bit, or we can use yield or return, but all of these are actually optional. So we could do async def and define a function and then just pass or return nothing. And that would still be a valid asynchronous coroutine. It wouldn't do much, but it would still work. Yield, what yield does is it returns a asynchronous generator, which we're not going to cover that much in this presentation. We're just going to focus on the use of await and return for kind of a more standard asynchronous coroutine. So what is the await keyword, which kind of goes hand in hand with this async keyword? So the await keyword signifies a part of the code that we can pause and while we wait for a result. So what the Python interpreter sees is once it gets to this await keyword, it's kind of saying, okay, I've sent off this request. It's going to take some time to come back, so I'm going to pass off the process for something else to be done. The CPU is like not blocked. So anything with the await keyword must be non-blocking, so it must not occupy the CPU in that time. And by it being non-blocking, that allows for other routines to execute while we wait for the result. So let's see it in action. So this is a pretty basic example of how you can use asynchronous code to kind of improve performance and execution. So what we have here is a very basic function called sleep for seconds. We make a print statement at the start of the function. We then sleep for a number of seconds, and then at the end we say we're done sleeping. The time.sleep is actually a blocking call. So for this synchronous execution, we'll use time.sleep. But when we get to the asynchronous execution, we'll use something different. So in this section, you can see when we're executing this code, we're basically going to sleep for 1 second, and then we're going to sleep for 2 seconds, and then we're going to sleep for 3 seconds. So if I just run that code now, you can see the start the sleep for 1 second, then the start the sleep for 2 seconds, and then the start to sleep for 3 seconds, each taking progressively longer. And that's just because this line should be commented out. But you can see what we've done is each function has executed sequentially one after the other. So it slept for 1 second, and then 2 seconds, and then 3 seconds. So the next function only starts when the previous one has completed. So if instead we look at an asynchronous execution, so this is this function here, this asynchronous sleep for seconds. The difference here is we've defined it using async def, which signifies that it's an asynchronous coroutine. And then we print the starting statement, so we're going to sleep for this number of seconds, and then we say await asyncio.sleep. So asyncio.sleep basically replaces time.sleep, but asyncio.sleep is a non-blocking call and allows the CPU to do other things. And then we have this await keyword here. So as soon as we get to this await keyword, Python will execute this line of the function, but then also back off from the process and say something else can execute. And then we say we're done sleeping after that number of seconds. And then if we uncomment this, so this is the asynchronous execution of kind of exactly what we had before. So we define a main function, which we use with the async def again, and then we just await this asyncio.gather. So this gathers all of the different tasks that we want to execute. So again, we've got the sleep for 1 second, we've got a sleep for 2 seconds, and we've got a sleep for 3 seconds. And we've gathered all of these tasks using asyncio.gather, and then we just use asyncio.run at the end to run this main function. So let's see that in action. You can see that all 3 tasks start at essentially the same time, and then they're done after 1 second, 2 seconds, 3 seconds. So as opposed to the previous execution of this, the previous execution would have taken 3 seconds for 1 + 2 + 3, whereas this execution only takes probably just over 3 seconds because all of the tasks can execute concurrently. Once it gets to that sleep stage, it just passes off the process to the other tasks. So that's a very basic kind of example of how you would write asynchronous code. I mean, clearly that bit of code there is not something we'd ever really use in practice, but you can see the theory of it. So now let's have a look at something which would be a little bit more realistic and what we might actually see in kind of our developing lives. So this is going to introduce aiohttp. So it's important to say that everything which I've showed you so far is part of the Python standard library. aiohttp you would need to install using pip. So aiohttp is an HTTP client/server framework that basically enables asynchronous requests. As a client library, it essentially just can replace the requests library, and it allows us to make asynchronous requests and then execute them concurrently. So we're going to use this module, and we're going to build a program that takes a list of IP addresses, is going to make an API request to ip-api.com to get information about that IP address. It's going to use this information to contact the 7timer.info API and get information about the temperature at that IP location. And we're going to try and make these requests asynchronously. So if we go to the file, so this is the implementation of that program. So we'll just go through the code line by line. In this first function, we get the IP data. Again, it's defined as an asynchronous coroutine. We use a session object, which we use to make our HTTP requests, and then we pass it an IP address. And we just have some print statements, and then we say the response equals, and then again, we use this await keyword, and we then say session.get, and we get the IP address. So what happens here is Python makes that request, and then it says, okay, it's going to take some time for the response to this request to come back, so I'm going to hand over the process and another function can execute. And then at the end here, we just return a JSON from that response. In this next function, we get temperature from the coordinates. So that previous function, there's a latitude and a longitude in the data that is returned. We then use that latitude and longitude, and again, we have this await keyword. So we say session.get, and we call this 7timer.info API. And then again, we're just passing over the process for something else to execute while we wait for the response. The headers on this response are actually not quite right. So for this one, we actually have to convert it to text and then use JSON.loads to get the JSON from. And then at the end here, we just return the temperature of the most recent timestamp as the result of the function. And then in this function, we're printing the info for an IP. And this is actually something quite powerful that you can do with asynchronous coroutines, is that we actually can chain these coroutines together. So we just pass this an IP address, and the first call is we get the IP data. Again, we use that await keyword, so we're happy to hand off the process while we get the IP data. And then what we do is we take that data from the IP data and we do feed it into the get temperature from coordinates. So we've chained together these two asynchronous coroutines, and it means that at any point between those coroutines, then the process can be passed over to something else. But this result still has to wait until this result comes in. And then we just print the IP address, we say what city it is in, the country, and we say the temperature. So we're going to look at how to execute this synchronously and then asynchronously. So obviously this code base is written asynchronously, but in this first execution, what we're doing is we use 3 asyncio.gather statements, one after each other. So essentially each one has to wait for the next one to execute and then the next one to execute. So what we've done here is we've kind of hacked together a way to execute this synchronously just for kind of demonstrative purposes. So I'm going to run that now, and we're going to see how long the code takes to execute. You can see we're making this first request, and this API, this weather API, actually takes a long time to respond. So it's quite a good example. But we get the data on the first IP, and then we get the weather data, and it takes quite a while. And then we have to wait for all of that to happen before we even start getting data from the second IP. Then we get the weather data for the second IP, and then again getting the data for the third IP, and finally the third one. So each one, again, only occurs sequentially, and we have to wait each time for the result to finish. But if we go back to the code, and then instead of executing it synchronously here, we're going to run it asynchronously. So here, what we had is 3 different await asyncio.gather statements, and one happened one after each other. In this one, we've just gathered them all together as one gather statement. So they're all gathered as kind of one task load, and then we just run it using asyncio.run main. So let's have a look at that. You can see we make all 3 of those IP address requests at the same time, and then we get the data from them back like very quickly after each other. And then again, now the function is complete, and we've retrieved all of that weather data at the same time. So all of that wasted time where we were just spending waiting for the request to respond, we've actually now massively improved the performance. So this has probably made it probably about 65% less time to execute. So you can clearly see that there is potential for pretty large performance increases just by using this asynchronous request and making sure that we're using that async keyword when we're making a request where we can actually hand off the process and allow other things to execute. So that kind of concludes the presentation. I hope you enjoyed it, and yeah, I'd like to open up the floor to any questions.
I've got one, Rafiq. So I think a challenging thing here can be if you've got a block of code that you're wanting to run in an async function, is there an easy way of identifying whether the code is blocking or not? Have you got any advice on that?
So often you need to actually find kind of asynchronous libraries that you can use. So for example, with database, like, well, in the example which I've just gone over is that we use aiohttp to make requests instead of the request library. I think that I was having a look at this for databases, and I think that of the SQL databases, it might be that Postgres, which is the only one which supports it natively. And there is for example, with Django as well, Django have just started to, as of 3.1, have started to support asynchronous requests. But for example, a lot of the ORM of Django, it doesn't yet support asynchronous requests. So it's definitely a bit of a balancing job of kind of looking through docs, finding different libraries that you use, and maybe it's something that is easier to do at the start of a project rather than having to kind of go through the whole code and change which function calls you're using to use non-blocking code instead of blocking code.
Yeah, it makes sense. And that's kind of what I expected, basically, that there's no hard and fast rule. But yeah, cool. Okay, it's interesting.
Yeah.
That. Thanks.
I am actually not aware if there's any kind of programs you can use to view which codes are blocking codes and non-blocking codes. It may be that you can run like a script and it will tell you where your blocking calls and non-blocking calls are, but I'm not sure if that exists.
Sounds like something you could be building, huh?
Yeah. Any other questions?
I think if no one has any more questions.
Okay, well, if there's no other questions, I think we can probably wrap this up. Thank you everyone for listening.